All right, now is 18.6, which is the last section of lecture for this week, occurrence, preparation, and properties of carbonates. And here we're going to describe the preparation, properties, and uses of some representative metal carbonates. So all of our metals in group 1 and 2, and then zinc, cadmium, mercury, and lead 2 form ionic carbonates. These are compounds that contain carbonate anions, which is CO3 2-. We can form them by reacting a metal oxide or hydroxide with carbon dioxide, with magnesium carbonate being an exception. So for instance, we can take sodium oxide and give it some carbon dioxide to give us sodium carbonate. Or for instance, calcium hydroxide and carbon dioxide. And this gives us calcium carbonate and water. The carbonates of alkaline earth metals, them from group 12 and lead 2, are not soluble, not soluble. Wow, okay. Soluble, and they will precipitate out of a solution when you take some soluble alkali metal carbonate and mix it with a soluble salt of the metal. Couple examples, if we take some Ca2+ and mix it with some aqueous carbonate, that gives us calcium carbonate, which is not soluble in water. You could do the same thing with lead. Calcium carbonate, the reason I use that for an example is this is what most pearls are made of, as well as the shells of mollusks. There's actually a professor at UC Riverside, I did not work with him, but he was in my department in chemical engineering, who would look at the structure of a lot of shells of invertebrates, namely sea creatures actually, to engineer stronger materials. So cool stuff. Actually, he's the reason mantis shrimp became like a thing for a while. The alkaline earth carbonates dissolve in water when that water has carbon dioxide in it, and this ends up forming hydrogen carbonate salts, and this is how caves and sinkholes form in limestone. So the metal hydrogen, the alkaline metal hydrogen carbonates saturate a solution of hydroxides with carbon dioxide, and then you can always evaporate out to these solids. So these alkaline earth carbonates now will dissolve in water. They're insoluble in pure water, but they dissolve in water with calcium dioxide, like I was saying. And they dissolve because we can form hydrogen carbonate salts. So we take some calcium carbonate, and then we've got some aqueous carbon dioxide and water to give us Ca2+ and HCO3-. So when it dissolves, then it can form these sinkholes. And then we can have these hydrogen carbonates of alkaline earth metals that stay stable only when they're in solution. As the solution, though, evaporates, the carbonate stays behind, and this is where we get stalagmites and stalactites in caves, because they were actually deposits of calcium carbonate. Sodium and calcium carbonates are the ones that are used the most as far as commercial uses. We can get sodium carbonate from what is called the mineral named trona. And then we can remove the impurities and recrystallize it to get the sodium carbonate. Sodium carbonates are fairly strong bases. They're not strong bases, but they're better bases than like most weak bases. You put them in water, they make a basic solution because that carbonate ion will accept hydrogen. So we have your carbonate ion, and then we've got our water, and we have our equilibrium to give us HCO3-. and OH minus. They'll react with acids to form metal salts, carbon dioxide, and water. And this is how something like Tums, the antacid, works. It's calcium carbonate. It is going to react with hydrochloric acid, which is your stomach acid. So when your stomach has too much of it, you take some Tums, and it helps to neutralize that acid into carbon dioxide gas, water, and a salt. You might burp a little bit. It's also used in glass making as a source of oxide ions. We also have bicarbonate ions, or hydrogen carbonates, and these can form from the metals in group 1, and then magnesium, calcium, strontium, and barium. And so these, like I said, have the hydrogen carbonate ion, also known as bicarbonate. Bicarbonate's probably the more well-known name, HCO3 minus. We can make this by saturating a solution of an alkali metal hydroxide with carbon dioxide and then evaporating water from the solution, which then gives us our solids. Where am I? Let's see. Where did my page go? Here it is. So we take some OH minus from our hydroxide and give it some CO2, and that gives us HCO3 minus. And then if we evaporate the water off, then we're left with this bicarbonate salt. The alkaline earth metal hydrogen carbonates are stable only in solution. Oh, sorry, I jumped a little bit ahead of myself with the last section, sorry. Stalagmites and stalactites are hydrogen carbonates. They're not carbonates. So carbonates give us our sinkholes and caves. Hydrogen carbonates give us stalagmites and stalactites when the water evaporates, leaving us with our alkaline or hydrogen carbonates now that are no longer stable in solution. Hydrogen carbonates are amphoteric. They can act as both a weak acid or a weak base. When they act as an acid, they form carbonate and water, and then they'll react also with soluble hydroxides. When they react, they form carbonate and water when they act as an acid, and react with hydroxide. So for instance, we take potassium bicarbonate and react it with potassium hydroxide, and we get potassium carbonate and water. When they react with acid and act as a base, they form a salt, carbon dioxide, and water. One bicarbonate that most of us know and have probably used is baking soda. Baking soda is also known as sodium bicarbonate. So we also have baking powder, which is baking soda and also has a solid acid. Normally it's cream of tartar. I didn't feel like putting cream of tartar as like chemical name. And so when they're solids, nothing happens, they exist together. But once they're in solution, so once you add water to your mixture, they're going to react and form bicarbonate ions and carbon dioxide. So then when you use either of these, depending on what the recipe calls for, you make carbon dioxide and the dough traps it, which causes things to expand during baking and giving you the characteristic baked good texture. So this is why there's little holes and stuff in your breads and cakes, and that's from the carbon dioxide expanding and getting trapped and then potentially leaving. So here's a stalactite on the left and stalagmite on the right. I always got it mixed up, but stalactites are the ones above you and mites are on the floor. And these come from, should be calcium bicarbonate, not calcium carbonate, I thought. Nonetheless, I'm not going to ask you guys about that. Here's calcium carbonate reacting with hydrochloric acid, so you can see those bubbles from the hydrogen gas that's forming, or sorry, not hydrogen gas, CO2 forming. And that does it for the first half of chapter 18. I'm sorry, I know it's a lot of talking at you, but we're almost done. Well, halfway done.